this video, I will present a method to separate the losses of a PEM fuel cell into each polarization component and to estimate the current operating state of said fuel cell. The method proposed in this study is designed for estimating the current state of the fuel cell using only its IV curve and confirming how the loss components represented by activation, ohmic, and mass transport loss change when the state of the fuel cell changes. The method presented here is developed based on independent component analysis, a method that separates multivariate signal into statistically independent subcomponents. In order to understand independent component analysis well, it is important to be familiar with the central limit theorem. This is because the concept of IC is kind of the opposite concept of CRT. The core content of CRT is that the distribution of a new random variable consisting of a linear combination of independent random variables follows a Gaussian distribution. Among the CRT theorems, IC can be said to be most similar to the inverse concept of Lyafunov's theorem, because it allows the distribution of each component constituting a mixed signal to be different from each other. As shown in the figure, in order to find the signal S from the measured signal X composed of component S, we need to find the W, which is called the mixing matrix. Now it is possible to consider how to apply the method to fuel cell loss component analysis. In the proposed method, the mixing signal is the total voltage loss obtained from the performance curve, that is, the IV curve. We want to separate this total loss into subcomponents expressed as activation, ohmic, and concentration. To this, we need to find the previously mentioned mixing matrix W, and in this study, W can be found based on maximum likelihood estimation. It can be called MLE for short. The maximum likelihood estimation is a method of finding the parameters of the probability density function that maximize the likelihood function. When all x have the same probability density function and are independent, the likelihood function can be expressed as a kind of joint probability function, and the logarithmic function can be used for the likelihood function because the logarithmic function is monotonically increasing. By considering the relationship between the source signal S and measured data X, and by applying the logarithmic function for the convenience of calculation, the likelihood function used in this study can be presented as shown on this slide. Conventional MLE, its mean maximum likelihood estimation, optimizes the probability density function parameters of the subcomponents, but we can observe that in this study we use the mixing matrix W and its elements as optimization parameters. The completed likelihood function is used as a cost function in the optimization process. In conventional ICA, the sigmoid function is used as cumulative density function of sources. This is because estimating the probability distribution function of sources is impractical in most cases or even too difficult to obtain. However, in our proposed method, the probability density functions of which loss components of the fuel cell was estimated by applying the Corner distribution function from the PEM fuel cell experimental data and used for optimization. Through this, not only the accuracy of the loss component analysis can be improved, but also result in broken down of the loss component related to actual loss can be obtained. The distribution function of activation, ohmic, and mass transport loss can be estimated through Corner distribution estimation. The precision of the estimated function varies greatly depending on the type of corner used for function estimation. In this study, we used the applications.The corner. And in order to increase the state discrimination and resolution of the proposed method, in addition to finding a weight W given to each loss component, we introduced the skewness and kurtosis concept. First, let's consider skewness. According to the definition in probability theory and statistics, skewness is a matter of the asymmetry of the probability distribution of a real-valued random variable about its mean. The skewness value can be positive, zero, negative, or undefined. For unimodal distribution, negative skew commonly indicates that the tail is on the left side of the distribution, and positive skew indicates that the tail is on the right. In cases where one tail is long but the other tail is fat, skewness does not obey a simple rule. For example, a zero value means that the tails on both sides of the mean balance out overall. This is case for asymmetric distribution, but can also be true for an asymmetric distribution where one tail is long and thin, and the other is short but fat. On the other hand, kurtosis is a matter of the tardiness of the probability distribution of a real-valued random variable. Like skewness, kurtosis describes a particular aspect of a probability distribution. There are different ways to quantify kurtosis for theoretical distribution, and there are corresponding ways of estimating it using a sample from a population. Different measures of kurtosis may have different interpretation. The standard measure of a distribution's kurtosis is a scaled version of the first moment of the distribution. This number is related to the tails of the distribution, that is peak. Hence, the sometimes seen characterization of kurtosis as peakness is incorrect. For this measure, higher kurtosis corresponds to greater extremity of deviations or outliers, and not the configuration of data near the mean. This slide shows the result of the total loss and each loss components obtained from the experiment in the form of a probability distribution. The red line you see in the graph is probability density function obtained using corner distribution estimation method. As explained before, it can be confirmed that the total loss, which is expressed as a linear combination of the three main loss components according to the central limit theorem, has a Gaussian distribution. Using the probability density functions of mixed signal and each loss component obtained from the experiment, the weight W can be determined according to the fuel cell state. Although the state change of the fuel cell can be estimated only with the W determined in this way, the state change of the fuel cell can be estimated more precisely by adding the change in skewness and kurtosis. In an article published early this year, the validity was verified by applying the proposed method to the data obtained through the theoretical model and to the experimental. These are the data simulating various actual fault situations. However, in this presentation, I will only briefly introduce the application later to the theoretical model. First of all, we verified how the proposed method works by increasing the size of the activation loss dominantly from the normal state. As is expected, it was confirmed that W1 assigned to the activation loss showed the largest change, and at this time, changes in kurtosis, skewness, and mean were confirmed as shown in the table presented. And when the magnitude of the ohmic loss was increased, it was confirmed that the W2 assigned to the loss component had the largest range of change, and the corresponding changes in kurtosis, skewness, and mean are shown in the table in page in this slide. Yeah. Thirdly, when the concentration loss was mainly changed in the theoretical model, W3 shows the largest change, and similarly, changes in kurtosis, skewness, and mean were confirmed as shown in the table below. The results of applying the proposed method to the theoretical model are finally presented on this slide and summarized into these three main bullet points. First, according to the change of each loss component, it is confirmed that the corresponding weight shows the largest increase. In other words, the weight given to the loss component showing the most dominant increase shows the largest increase in the first direction. The second, as skewness changes to negative values, W1 increases and W3 decreases as a counter benefit. The opposite occurs when skewness increases. This is a phenomenon caused by the symmetric characteristics of probability density functions of activation loss and concentration loss. And this relationship between skewness and W1, W3 can be used for state identification and can increase the resolution of state estimation. Lastly, as kurtosis decreases, W2 increases. When kurtosis is lowered under the same variance, it has a shape similar to a uniform function. Since the probability density function of the ohmic loss has a unimodal shape, the weight increases toward 1 as the distribution has lowered kurtosis by the definition of kurtosis and the characteristics of likelihood function used. The opposite occurs when kurtosis increases. For more detailed information on the proposed method or experimental results, please refer to the following paper or feel free to contact me to this address. Thank you for your attention.